Hello everyone. We will now begin our lecture on section 5 of chapter 3 on logic, and today we learn about symbolic arguments. Now, symbolic arguments are nothing but a set of premises followed by a conclusion, and premises are really statements. Could be a bunch of compound statements or simple statements, and based on those statements, or also known as premises, we can arrive at a certain conclusion, which is also called an argument. And with the help of logic, we can decide whether a certain conclusion drawn from the set of premises that was given to us, whether the argument is valid or whether it is faulty, whether there's a fallacy in it, and so on. All right, so in this chapter, we will learn the process of coming to conclusion on arguments, and then whether the argument is logically valid or not. So these are some of the things that we will learn in this section. First of all, we will learn how to determine the validity of a symbolic argument by using truth tables or by using standard arguments, and then we will learn to determine a logical conclusion from a given set of premises. So what is symbolic arguments? A symbolic argument consists of a set of premises and a conclusion. It is called a symbolic argument because we generally write it in symbolic form to determine its validity. In other words, an argument is composed of a set of premises which are nothing but statements, a set of statements, and following those statements, we arrive at a conclusion, and the whole set of premises and conclusion together form an argument. So just to give you an example, I'm going to set up an argument with two premises. Again, premises is nothing but a set of statements. All right, so I'm going to have two premises. Premise 1 is going to be represented by the letter P, and it's going to say if it rains, the picnic will be cancelled. All right, the picnic, if it rains, the picnic is cancelled. And then premise 2, which I'm going to represent with the letter Q, says the picnic is cancelled. The picnic is cancelled or was cancelled, whatever is cancelled. All right, now given these two premises, we can come to what's called a conclusion. And a conclusion is denoted by the therefore symbol, all right, which is three dots in a triangular form. So the conclusion could be that it rained. All right. So that's the conclusion. Now, everything together forms an argument. And then at the end of it, we have to go and test whether this conclusion, this entire argument, is valid or not. And in order to do so, we will put these statements in symbolic form and then create truth tables, and then run through the process of coming up with truth values, and eventually that'll help us determine whether the argument is valid or not valid. If it is not valid, we use a term called fallacy. All right, there's a fallacy in the argument. So we are going to learn here how to go about that process of validating an argument and deciding whether it is correct or whether it is incorrect, right? So again, arguments can be valid or invalid. An argument is valid when its conclusion necessarily follows from a given set of premises. And an argument is invalid or it's a fallacy when the conclusion does not necessarily follow from the given set of premises. All right, so this is a definition of what is considered to be a valid argument versus an invalid argument or a fallacy. Now, when validating arguments, we use different laws based on the way the argument is set up. Remember that arguments consist of a set of premises followed by a conclusion, right? So the first law that we learn of is the law of detachment. In Latin, it's also called modus ponens. So we will present here a set of premises symbolically written out. So symbolically, the argument is written as premise 1 being if P then Q. So that is a conditional statement, and premise 2 will be just P. So based on these two premises, we will arrive at a conclusion which is therefore Q. All right, so this symbol here, the therefore symbol, represents the conclusion which is Q. Now, the law of detachment says if premise 1 and premise 2, then it is Q. All right, that's how we put it in words. So let's pull up the detachment law here. If premise 1 and premise 2, then the conclusion. And so based on these premises and conclusions, we see over here the symbolic representation, which is within square brackets, if P, then Q, and P, all right, these two premises joined by the and symbol, then the conclusion is Q, all right? Now, before we go into working an example on validating an argument, we're first going to walk through the steps, the step-by-step process of validation. All right, so we start by writing the argument in symbolic form. That's the first step. So the argument will be given to us in the form of words, and keep in mind the argument is not just the conclusion, but it is the entire set of premises as well as the conclusion. So all of them must be put together in symbolic form. And once we do that, step 2 is to compare the form of the argument with forms that are known to be either valid or invalid. If there are no known forms to compare it with, or you do not remember the forms, go to step 3. All right, so I've just read through it, but once we work through an example, it will make more sense. This second step, let's go to step 3 at this point. So the step 3 says, if the argument contains two premises, write a conditional statement of the form premise 1 and premise 2, and then followed by the conditional symbol and then the conclusion. All right, so it reads as if premise 1 and premise 2, then the conclusion. All right, so this is what the law of detachment was. This is of the form which was the law of detachment. In step 4, it says construct a truth table for the statement above. So let's see what step comes after that. Now, in the final step, we will look at the truth values that come from the truth table we created in step 4. And if the answer column of the truth table has all truths, then the statement is a tautology and it says the argument is valid. If the answer column of the table does not have all truths, the argument is invalid. All right, so this is how we are going to arrive at a conclusion whether the argument is valid or not. All right, so in the next slide we will work through, or in the next few slides we'll work through an example of validating an argument. So here's an example that we will work through to determine the validity of an argument with a truth table. All right, so they've given us the following argument. Again, argument should consist of premises and a conclusion, right? So they have given to us the premises as well as the argument, or rather as well as the conclusion in word form, in the form of statements. So we will first have to rewrite these in symbolic form, correct? That was the first step in the process of validation. So the first premise is if you have enough reward points, then you get a free flight. And the second premise is you do not get a free flight. And then the conclusion is therefore you do not have enough reward points. So we'll perform the first step here before we go to the next slide to see how they have written it in symbolic form. If you have enough reward points, so first thing is to put everything in premise and conclusion form. All right, so here I'm going to write P, which is going to be premise 1. P is stating the statement, the first part of the if condition is to have enough reward points. So you have enough reward points. All right? Reward points. And then Q will state you get a free flight. You get a free flight. All right. And then from there we have the conclusion, you do not have enough reward points. All right. So let's write it next to each of these statements. If you have enough reward points, so there's an if statement here, then you get a free flight. So in other words, this is going to say P, if P followed by this one directional arrow, if P then Q, correct? If you have enough reward points, then you get a free flight. And then the second premise is you do not get a free flight. So how are we going to write that? Q is you get a free flight, and this one has a not, so you're going to say not Q, correct? Not Q. And then the conclusion is therefore you do not have enough reward points. So we have to write this also in symbolic form. You do not have enough reward points, which is the negation of P, correct? So that's going to be not P. Okay, so when we put together all this, we will come up with a complete symbolic statement, all right, with conjunction and everything. And then we will have to create a truth table. But let's go on to the next slide to see how they have worked the first step of the process. All right. So here we have the solutions that they have given us, and let's see if that matches with the way we were approaching this problem. All right, so here they have broken up the premises into two individual simple statements. P represents you have enough reward points, and Q represents you get a free flight. All right, that's exactly what we had done previously. And then we are going to put each of those statements in symbolic form, which is if P then Q. The first one was a conditional statement saying that if you have enough reward points, you get a free flight, right? And the second premise was you do not get a free flight, which was a negation of Q, correct? Q was you get a free flight, and the premise was you did not get a free flight. So it was a negation of Q, and that's why we have the negation not Q symbol. And then for the conclusion, we have the therefore symbol. What was the conclusion? If you recall, it said that you do not have enough reward points. And that was a negation of P, so that's why we have it as not P. And now we are going to put everything together with a conjunction and write the entire argument. At this point, it's an argument, all right? So this symbol for the argument is if P, then Q, and not Q, then not P. So there's an if, nested if statement. All right, so there are two conditionals here. So if is for this condition, and then we go to inside of the square brackets, which is if P then Q, and this is the conjunction symbol, and not Q, which was the second premise, then it's not P. So the argument, or rather the conclusion, goes on the right hand side of the conditional symbol here. All right. Now over here in the next step, we are going to build a truth table out of the statements we created from the argument, out of the symbolic statement that we created from the argument in the previous slide. All right. Now this particular statement does not conform to the law of detachment that we had learned. If it had, then we could have just used that law, but this one doesn't fit that law, because if you recall, that law said it went like this. All right, it went if P if P then Q and P then Q. All right, but this is kind of different. It says if P then Q and not Q. All right, it doesn't have the P. It says not Q, then not P. All right, so this was the law of detachment that I wrote up here, but what we are given doesn't fit this model, doesn't fit this law. It actually, we will see there's a different law for this, but since we cannot apply the law of detachment, we are going to just go ahead and construct a truth table with this, and then if all are true, we will know that the valid, or rather the argument is valid. It's a tautology. Otherwise, it isn't. All right, so let's go through the process. I'm going to just pull up the solutions here. So the first step is to work on the nested if P then Q statement, the conditional statement, which is within the brackets of the square bracket. All right, so that's the first step. So we have here on the left hand side the two columns for P and Q and the combinations of all the true and false values put together. So if P then Q will come up like this. If it's true, it'll be a true. All right, if it's true and false, it'll be a false. If it's false true, it'll be a true, and if it's false, it'll be a true. All right, so recall that if in a conditional statement, if the if condition is a true, but the then condition is a false, that's the only time when the truth value is a false. All right, so the second part of it, we are going to evaluate not Q, which is simple. We'll just have to reverse the true and false values over here. So the true will become a false and the false will become a true in not Q. So let's pull that up. So here we have the second part of it. False, then we should have a true followed by a false and then a true. All right, and then we work the conjunction here, which is the and statement. So recall that the only time that the and statement will result in a true is when both values are true. All right, otherwise it will be a false. So let's see if that's what happens. True and false should come up with a false. All right, that's the third step. All right, true and false comes up with a false. False true should be a false. True false should be a false, and true true should be a true. All right, and now we have to evaluate. All right, over here, not P. All right, so not P should come up as step 4. So we have to just reverse all the true and false values under P, under the column P, and make the trues a false and false a trues. All right, so for the first one, it should be a false followed by a false followed by a true followed by a true. correct? And now we have to go and evaluate this if condition. But what are we using? Which columns are we using? Let me highlight that. All right, so we are using this column here under the and this column under the not P. All right, not P. And again, this is conditional, so only when the if condition is true and the then condition is false, it'll be a false, otherwise everything will be a true. All right, so let's see what values come up here. So the first one is false and false, correct? False and false should be a true. Is it a true? Yes, it's a true, correct? The next one is false followed by a false should also be a true. All right, so it's a true, and then false and true should be a true. And finally, we have a true, and a true should be a true. All right, so we find that all of these are true statements, or the values are all true, therefore it makes it a tautology, and if it's a tautology, then the argument is valid. All right. Now we will go through a set of standard forms of arguments which will always lead to a result of valid arguments. All right, so there'll be 4 laws, and we already learned about the law of detachment previously, and that was if P then Q. If the first premise is if P then Q and the second premise is P, then the conclusion, if the conclusion is Q, then it's a valid argument, and this form of the argument is called the law of detachment. All right, then there's another one called the law of contraposition, and this structure, as you will see when I pull up the results, is same as what we worked through in the previous example. All right, so the first premise in the law of contraposition is if P then Q, and the second premise is not Q, then the conclusion is not P. If this is the construction, if this is the form of the argument, then it will always be a valid argument. Let's pull up the third one here, which is the law of syllogism. Now in the law of syllogism, what it says is if P then Q, as is the first premise, and the second premise is if Q then R. So as you realize here, we have 3 statements, not 2, 3 statements. If P then Q, and followed by the second premise if Q then R, then the conclusion is if P then R. So if this is the construction, then it is a valid argument and falls under the law of syllogism. And then we have the disjunctive syllogism, and so let's see what that brings up. The structure of that is P or Q as the first premise. The second premise is not P, all right, not P. Then if the conclusion is Q, all right, therefore Q, if that's what the conclusion is, then it is again a valid argument and it falls under the law of disjunctive syllogism. All right. Now we look at some standard forms of arguments which will always be invalid. In other words, which will always result in a fallacy. All right. So the first one is the fallacy of the converse. So let's pull that up. The structure is if P then Q, being the first premise, followed by the second premise, which is Q, therefore P. This will never be a valid argument. It will always be an invalid argument, resulting in a fallacy. And it's called the fallacy of the converse. Then we have another one, which is the fallacy of the inverse. So let's pull that up. It's structured this way. If P then Q, the second premise being not P, P, the negation of P, and then the conclusion being not Q will always result in an invalid argument, causing a fallacy of the inverse. All right, so recall how we decide whether something is true or something is valid, an argument is valid or invalid. We construct truth tables, right? We construct truth tables with a conjunction, and then we see if the final truth values are all true. If it's a tautology, it is a valid argument. However, if any one of them is a false, then it will result in a fallacy, in an invalid argument. Let's look at this example here to determine whether the following argument is valid or invalid. So let's read through the premises. We have premise 1. All right, so this is premise 1. Then we have a second premise, and then we have the conclusion, right? But we first have to put them in symbolic form, all right? But let's just read through the premises first, all right? It says here, if you are on Instagram, then you see my pictures. And then the second premise says, if you see my pictures, then you know I have a dog. And then the conclusion says, if you are on Instagram, then you know I have a dog. All right. So first, I'm going to break each of these compound statements, conditional statements, in simple atomic statements. All right. So there are 3 statements that we can come up with from the following statement. So P will represent being on Instagram. All right, so you are on Instagram. And then Q will represent you see my pictures. You see my pictures. All right, that's Q. And then the third one is I have a dog. All right, or you know I have a dog. I have a dog. All right, so based on these simple statements, let's see how we can put together the first premise in symbolic form. Again, it's an if statement, correct? So it's going to be a conditional statement. If you are on Instagram, so which is the one P, right? So if P, so P followed by the arrow, one directional arrow, and then you see my pictures is Q. So if P, then Q is the first premise. All right, premise 1. The second premise is if you see my pictures. So if you see my pictures is Q. So if you see my pictures, then you know I have a dog. So that's R, correct? So the second premise is if Q, then R. So, and what is the conclusion? How can we write that in symbolic form? It says if you are on Instagram, so let's write it like this. Therefore, now if you are on Instagram, it's P. So if P, then you know I have a dog. If P, then R. All right. So given this argument now in symbolic form, let's see how we can go about the process of figuring out whether it's a valid argument or an invalid argument. Now we look at the solution, all right, of the argument that we put in symbolic form, and we will see that it fits a law, one of the laws of valid arguments. It was called the law of syllogism, and by that it should be a valid argument. In that case, if we can identify that the argument fits one of the laws of valid arguments, then we do not need to go through the process of constructing tables, truth tables and all that. All right, we can just use that law to come to the conclusion that it's a valid argument. All right, so let's pull up the results here. Over here it says P, the simple statement denoted as P would be you are on Instagram, which is just exactly what we said. Then Q is you see my pictures, and then R is you know I have a dog, right? And then we construct the symbolic form of it, which is if P then Q, followed by the second statement was if you see my pictures, you know I have a dog, which is the second premise, followed by the conclusion, which is if you are on Instagram, then you know I have a dog. All right, so this is the law, this fits the law of syllogism and therefore is a valid argument. All right, so this is how you apply the different laws of valid arguments to come to a decision whether the argument is valid or invalid without having to construct truth tables. Now let's look at an example where we will be applying the laws of fallacies that we learned about. All right. So there were two laws of fallacies. One was the fallacy of converse. The other one was the fallacy of inverse. So the question says here, determine whether the following argument is valid or invalid. If it is snowing, then we put salt on the driveway. That's the first premise. The second premise is we put salt on the driveway, and the conclusion is therefore it is snowing. All right. So let's again put everything in symbolic form. So we'll start with writing the simple statements out of these compound statements. So P will be it is snowing. That's the first atomic statement here. It is snowing. And then Q, the other statement will be we put salt on the driveway, right? Salt on driveway. Now let's write each of these statements or premises using P and Q. So if it is snowing, so that means it's a conditional statement. If P then Q is represented as if P then Q, correct? And then we put salt on the driveway is Q, correct? So that's Q, which leads to the conclusion that it is snowing. That means it is P. All right, so actually let me rewrite this a little bit. I'm going to write the P, if P then Q over here, and then Q followed by the conclusion, which is therefore P. All right, so we will see that this is actually a fallacy. So let's go to the next slide to pull up the solutions and see which fallacy it is, which will render this as an invalid argument. So let's pull up the solutions here. First, we will set up P as it is snowing. That's the first simple statement. Then Q is we put salt on the driveway, followed by, in symbolic form, the argument is if P then Q. That means if it is snowing, we put salt on the driveway, followed by the next premise, which was we put salt on the driveway, followed by the conclusion that it is snowing, right? That's what P is. However, it is in the form of the fallacy of the converse. So that's the law of the fallacy of converse, which will make it an invalid statement. All right. Now, how could we make this a valid statement? What changes would we need to do here in order to make it a valid statement? One way of doing that is we keep the first premise the same. All right, let me pull up another color here. We keep the first premise the same, if P then Q. And instead of this Q, if we make this a P, all right, the second premise, if that's a P, and then if we make our conclusion Q, then it fits the law of detachment, which is a valid argument. All right, in this case, this would have been valid, but this is a fallacy. All right, so let's once more look at the law of detachment here that we use to change the fallacy to a valid statement, valid argument. So if it is snowing, then we put salt on the driveway. The second premise is it is snowing, therefore we put salt on the driveway. All right, this was the law of detachment. If we phrase our argument this way, in this form, then we can say it is a valid argument. However, the way it is stated in this example, if P then Q, followed by the second premise of it is snowing, we put salt on the driveway Q, uh, and come to the conclusion that it is snowing, that would be a fallacy. All right. Now let's look at another example of a fallacy in arguments. Here we have two premises. If it is snowing, then we put salt on the driveway. And then the second premise is it is not snowing. The conclusion is therefore we do not put salt on the driveway. So there are two, and they use the same statements pretty much. It is snowing, that's P, and we put salt on the driveway is Q. All right, given that the symbolic form of the conditional statement will be if P then Q, followed by it is not snowing would be not P, and then for the conclusion, which is we do not put salt on the driveway, is therefore not Q. Correct? So let's see if this is a fallacy and which law of fallacy it fits. All right? So here's the solution. The first step is to put them in simple statements. P being it is snowing, Q being we put salt on the driveway. In symbolic form, the argument is if P then Q, and the second premise, if P then Q was if it is snowing, then we put salt on the driveway. The second premise is not P, that means it is not snowing, followed by the conclusion, which is not Q, correct? Which means we do not put salt on the driveway. And then we see that this construct is in the form of the fallacy of the inverse, and therefore it is an invalid argument. All right, so here we didn't need to construct truth tables. We didn't need to go through that process. By just recognizing that this argument fits the form of the fallacy of the inverse, we came to the conclusion that it's going to be an invalid argument. All right. Finally, we'll work through an example, rather an argument with three premises. All right, so let's read through it. First, it says use a truth table to determine whether the following argument is valid or invalid. So here, instead of going by the different laws of valid arguments or invalid arguments, fallacies, we are going to construct a truth table to come to a decision whether it's valid or invalid, and we have three premises here. All right, so let's go through the different premises given to us. The first one says if my cell phone company is XYZ, then I can call you free of charge. The next premise is I can call you free of charge, or I can send you a text message. That's the second premise. The third is I can send you a text message, or my cell phone company is XYZ. And all these three premises lead to the conclusion, therefore, my cell phone company is XYZ. So again, first let's break it up into three statements, and then we will write the entire argument in symbolic form. So the first statement is that my cell phone company is XYZ. So let's call that P. All right, cell company is XYZ. And then the second one, Q, right? The Q, what is it? It says I can call you free of charge. So I can call free. All right, and then the third one, PQR, PQR says I can call you free of charge, or I can send you a text message. All right, so send a text message, or can send a text message. All right, so given these three statements represented as PQR, let's try to put this argument in symbolic form. The first one is an if condition, is a conditional statement. If my cell phone company is XYZ, that means if P, then it should be Q. I can call free of charge, correct? So let's write that as P. If P, then Q for the first one. And then the next premise is I can call you free of charge, or I can send you a text message. So here we have the or statement. So I can call you free of charge is Q, correct? And then send you a text message is R, and there is an or in between the two, so Q or R. And then the third premise is I can send you a text message. I can send you a text message, and that would be R, or my cell phone company is XYZ. So how do we write that? I can send you a text message is R, and then there's an or here, so or, and then company is XYZ is P, correct? So it's going to be R or P, and therefore the conclusion of all these premises is my cell phone company is XYZ, so it's going to be P. All right, so we are going to put all these three premises together. So if P, then Q, and Q or R, and R or P, and then on the right hand side we are going to have the P, and then we'll finally have the constructed truth table tell us whether it's a valid argument or not. So let's go through the solution. It should be pretty much the same as what we came up with. First of all, P represents my cell phone company's XYZ. Q represents I can call you free of charge, and R represents I can send you a text message. In symbolic form, the argument, the first premise is if P then Q. That means if my cell phone company is XYZ, then I can call you free of charge. Then the second one is Q or R. That means I can call you free of charge, or I can send you a text message. And then the third premise is R or P. That means I can send you a text message, or my cell phone company is XYZ. And then what was the conclusion? It said that therefore P, which is my cell phone company, is XYZ. All right. So the entire argument has to be written in symbolic form, and here it is. If first of all there is a nested square bracket here which is not initiated at the right hand side, so I'm going to write that here. All right, just a second. All right, yeah. All right, so it has to be paired up. So what do we have inside the square brackets? If P, then Q or and Q or R, and R or P. All right. And then the conditional leading to a P. That's the argument. That's the conclusion, really. All right. So if P, then Q, and Q or R, and R or P, then P is the right way of reading this. All right. So next step is to construct the truth table. So let's look at the truth table for three premises. As you can see, this is quite an extensive table. We have the three premises listed out on the left hand side, and all the combinations of truths, true and falses, the truth values for three premises here. So there are about 8 combinations, correct? And then over here on the right hand side we have the entire symbolic argument put in columns, right? So we have the conditional, the nested conditional, if P then Q, followed by the conjunction with Q or R, and then another conjunction with R or P, and then the outer if condition, which results in a P, the conclusion. All right. So how do we go about step by step through this truth table construction? The first step is over here. You see number 1 is the first step to evaluate the nested if condition, if P then Q. And then the second step would be to evaluate Q or R. And then in the third step, we first evaluate the conjunction between if P then Q and Q or R, correct? And then for the fourth step, we evaluate R or P. And then for the fifth step, we evaluate this conjunction. And then for the sixth step, that is, we look at our P values. We list all the P values, all right, from the first column. And then finally, we evaluate the outer conditional. So let's go through it step by step, all right? So the first step was to evaluate if P then Q, and for that we refer to these two columns here, right? These two columns. So this is an if condition. Recall that in an if condition, the only time that you get a false is when the if condition is a false, is a true, and but the then condition is a false. All right. Sorry, what I meant to say is if the if condition, the first what is called the antecedent is a true, but the consequent is a false, that's the only time we get a false for a truth value. Otherwise, it's always true. So let's look at this. True, true should give us a true. True, true, a true. True, false should result in a false. All right, the if is a true, but the then is a false. That's the only time it'll result in a false. True, false gives a false. False, true should give a true. All right, false, true, a true. False, false should be a true, and false, false is a true. So first step is completed. Next is to go to step 2, which is evaluate Q or R. Now, in the or statement or a disjunction, what happens is the only time that you get a false is when both statements are false. All right. So true. All right. Q or R. First, let me color and make it explicit which two we are looking at this time. All right. To avoid any confusion, as you can see, this is a rather complicated truth table, and it's very easy to trip here. All right, so let's see. It's Q or R, correct? So true, true should be a true. All right, true, false should give a false. Only time it'll be a false is when both are false. False, true should be a true. False, false should be a false. True, true should be a true. True, false, a true. False, true, a true. Again, when you have two falses, it results in a false. All right, so second step is now completed. We have to find the conjunction of the nested conditional and this or statement. All right, so now we are looking at which two columns here. Let's color that here. This one and this one. Now in an and situation, all right, when it's a conjunction, then the only time that something will be a true is when both are true, correct? So based on that, true, true should give us a true. True, true gives us a true. False, true, a false. False, false, false. True and true gives us a true. True and true gives us a true. True and true gives us a true. And true and false gives us a false. Or again, in a conjunction, only when both conditions are true, we get a true. Otherwise, we end up with a false. All right. If any one is a false, it is a false. It results in a false. All right. So we've completed step 3. Now we are going to go to step 4, which is to evaluate R or P. All right. So let's see which ones are we considering now. Right. R, I'm going to color R, and P. All right, R or P. So R or P would be, because this is an OR, the only time it'll be a false is when both are false, correct? So true, true gives a true, true, false gives a true, true, true gives a true, true, false gives a true, false, true gives a true, false, false gives us a false, false, true gives us a true, and false, false gives us a false. All right, so here we have this column. All right, the 4th column completed. All right, so what is the 5th column? The 5th column is to take the conjunction of which two values over here. All right, now we take the conjunction between this here. Right, so let me highlight it again, and I'm going to erase this and erase this. Okay, so now we are looking at this and this to come up with this conjunction here. All right, so what do we have here? We have, again, it's a conjunction. True, true results in a true, true, true results in a true, false, true results in a false, false, true results in a false, true and true results in a true, true and false results in a false, true, true results in a true, and false, false results in a false, correct? So let's circle that, or let's highlight that over here. All right, so we got this in step 5 as step 5, correct? Now we will go to step 6, which is just writing the values of P from the first column. And once we do that, we are going to evaluate the conditional here. So this time we are evaluating the conditional of these two. All right, these two. So I'm going to erase this, and just indicate over here we are looking at this and this. All right, and let's erase this to avoid confusion. All right, so let's start here. True, true gives us a true. True, true again gives us a true. Again, this is a conditional that we are evaluating. So the only time something will be a false is when the first one, the if condition, is a true, but the then condition is a false, right? So false, true should give us a true. False, true should give us a true. True, false is the only time it's a false. False, false gives us a true. True, false gives us a false. And then false and false gives us a true. All right, so this is the last step, the 7th step. And then we go and look at the truth values and see if all of them are true. If all of them are true values, then if we would consider it valid argument, a tautology. However, here we see we have 2 false values, so that indicates that this is an invalid argument and therefore a fallacy. All right. So to summarize, as we saw from the truth table, that the final answer in column 7 is not true in every case. There were 2 false values, therefore the argument is a fallacy and therefore an invalid argument.